Hey everyone, I'm back with a new update on my 3D engine for 3DO called Matinicus. It's inspired by the game Killing Time. I would like to reiterate that I am only using Killing Time assets for testing my engine with. I have no plans on using any Killing Time assets for any projects. With that said, I now have added the base support for enemies in the game. At a top level, I'm referring to the different types of objects that you'll be interacting with as game objects. Now, in order to support the base foundation, I needed a way to store state information. So, for example, an enemy may be idle until it sees you, then it may try and chase you, and then it may try to engage you, things of that nature. And so with that, there comes information such as sounds that you need to keep track of, delays for animation, what that animation looks like. And so before I started working on this, I did a little bit of research on how Doom kept track of that information, and I really liked the way they do it. It's a little redundant. You'll see in a second. It's a little redundant with some things, but ultimately it's very simple to keep track of. It's very simple to update and extend and reuse. And so I went with that. So what you're looking at here is my state structure. And a state can be very granular. A state can be at an individual frame level, but you'll see that there's groups of state, such as when you're idle, or when you're moving, or when when the enemy is moving, or when the enemy is idle, so on. So with each state, there is a frame number. So this corresponds to which image to display. This tick delay is how long the engine should keep the game object in this state for. The next item here is a function pointer. So what logic should run while the enemy is in this state? And then finally, what's the next state that the enemy or the game object should enter after this delay? And so I have an array of states. We'll get to that in a second. And there's also a game object info chunk of information here. So different game objects will have different values populated for this structure. But for example, when an enemy spawns, how much health should it have? What's the, how big is it? What's the collision radius? What are the core states? So which state should the enemy enter when it's spawned, when it sees you, when it decides to attack? And there's going to be others. Along with what sounds to play, how much damage does this enemy cause? And so if we go to my states file, you'll see that at first it looks a bit confusing, but I'll break it down and it will be very straightforward. So you can think of each of these items really as a frame or a snapshot of an enemy or a thing or an object in a current state. So when the enemy is idle, there's only going to be one state entry that's going to repeat. And you can see here that for that entry, we're going to use image 1 for the frame, or frame 1. This next item would be a tick delay to the next state, but we don't care about that since this is just going to keep repeating this entry. We don't care about switching to a different state. Which function should run while in this state? And then finally, this is the next state in this table that is going to run. Now you'll see that this here, enemy 1, idle 1, this just comes back to the same entry in this table. So this is going to keep repeating. Now I have these little comments here, this little hat symbol, just to help visualize the grouping. So for example, when enemy one rather is in idle, this is the entry that will keep being executed or referenced. When the enemy has already seen you and is chasing you around, this is the block that's going to be repeating. So you can see that we show frame 1 for 4 ticks. We call the chase function. The next state, which is chase 2, is actually this entry down here. And then at the end of this execution, it's going to jump to chase 3, which is this entry. So it's going to proceed down, and then you'll see here on the last entry, it goes back to the first entry in this chunk. So this will keep repeating over and over again, as long as the actual top level main state does not change. And then you can see here the different frames of animation that it will cycle through at the different intervals. When the enemy decides to attack, now we jump to this chunk of state entries. So we go from attack, this is actually attack 1, but it jumps to attack 2 afterwards, to 3, 4, 5, 6. Shows different frames of animation. And then you'll see here that rather than repeat, it will jump back to the chase state, to the first entry in the chase state. And it won't come back to this group of states anymore until it's switched back over to attack. And what's really cool about this is I'm able to leverage the same concept for these enemies to even power the player's weapons. So I'll get to that in a second. I'll show that rather. But you see here that when the pistol is in its first state, this is the image it's going to show, 13, right? It's going to check to see if you fired your weapon. And if you fired your weapon, then it's going to cycle these other frames here and then go back to the very first state. So with this covered, let's take a look at this. Just populates the information blocks for the different objects. So here's player, here's item 1, which can be anything. I haven't really defined that yet. Here's enemy type 1. And you can see the states here, idle, chase, and attack, which get populated into these. And then the HUD pistol, or the player's pistol, you'll see that there's some redundancy where there's some information that not everything is going to use. For example, the pistol that you're firing is not going to have spawn health. So there's a little redundancy there. But I'm still going to keep it this way because it makes organizing this stuff pretty easy. So I'm going to sacrifice the redundancy for simplicity. But if we go to the things file, things are basically another name for a specific name for certain types of game objects. So these are going to be more of a concrete identifier for the enemies, but or maybe pickup items. But you'll see that when we were defining states, how we have these callback functions. So let's look at the search function here. So the search function is going to check to see if the player has made any noise, and if the player did, then it's going to activate. It's going to switch to the C state. If the enemy has not made any noise, then it proceeds to check for line of sight. We'll get to that in a second. But you'll see that at certain points, the overall state will change to a different grouping. So in this case, it goes to the C state. In this case, it will also go to the C state. While being chased, it has logic to go into an attack state. And this table here that we looked at previously is just constantly being referenced. Which animation to show, how long between the states, what's the next state entry to call. And some of this stuff is cyclic, right? Where like if you're in chase state, it keeps going back on itself. If you're attacking, it goes through the attack and then jumps back to state. So some of the states are set in code logic, and then some of the states are just cycled through this table until there's some sort of interrupt that changes it. So what I'll do first is I'll run through the program to give you just a visual of the enemies in the map. Now, right now they don't move, but they can see you and they can decide to attack you, although you can't take damage yet. And then we'll talk about how I tackle the line of sight code. So let's fire this up. Okay. So if I enter this room, you're going to hear a little growl. And he's attacking me. One thing that's pretty cool is that if you're not in their line of sight, they won't try and attack you. I know that sounds pretty basic, but some games just, you'll still hear the attacks. Like in Killing Time, you'll still hear the gunshots of these guys, even if you're hidden. But if I get back into this corridor here, this hallway, you'll notice that the shots stop. So I'll run around really quick because I have some other ones that are placed here. Got one there. So they start out in an idle state, and then they switch to a chase state, and then from chase they go back and forth between attack and chase. So if I come up here, I got some more guys hidden back here. You'll notice too that as they fire their weapon, the sound effect occurs right when you see the flash of the muzzle, and I'm able to control that precisely using that state table. And you'll notice that also their gunshots illuminate the scene, just like the player can. So that still needs some work. Obviously, it doesn't look like there's even a bullet leaving the gun, but yeah. So let's cover how the enemies know that I'm present. So the way I did this is a divide and conquer method. So Doom has a concept known as a reject table. I learned about that, and I also incorporated it because it's a pretty brilliant idea. But basically the idea is, if you're in a sector, let's bring up this image. If the player is over in this sector way up here, there's no way for an enemy way down here, for example, to see him. And a very quick way to test that condition is if you have a lookup table, and this lookup table represents, does sector A have line of sight into sector B? And so you can see this oddly shaped polygon here. This is sector, say, A, and this is sector B. Well, there's no way regardless of which point you're in this sector, it's impossible for you to look into this sector and vice versa. So Doom refers to this concept as a reject table. It's a table that you can do a quick check-in and say, can thing A see thing B based on information in this lookup, which is pre-calculated? And if not, there's no need to do any other checks. And this check is very fast because it's just a lookup into a table. So this, I was doing some research, and this is how that reject table is laid out, where you can think of the horizontal axis. This is assuming you only have 5 sectors in a map, but this horizontal axis represents the sector that the player can be in, or an enemy, and the vertical axis represents whether or not the sector has line of sight into the other sectors. So you see you have sectors 0 through 4 and then 0 through 4. So if players in sector 1, can the player look into, can the enemy look into sector 0, which would be this first entry here, and the answer is no. Or actually, the logic is flipped. If there is a one, if there is a one bit in this table, that means reject to test. The whatever you're testing cannot see into the sector. If it's a 0, then the check is not rejected. But this is a way to quickly do a lookup. And the data is stored in bits. So even though the map could be large and even though there can be many sectors, all the bits are being packed in essentially, and the lookup is at the bit level. So it's compressed. So this is the reject table check right here, sector line of sight. And here I grab the sector ID for the enemy, and then the sector ID that the player is in, and it does a check. Now, if that check passes, it means that there's line of sight at a sector level. So the next thing that I do is a field of view check. I don't know if Doom must do something similar. I haven't looked. But my field of view check will compare, it will take the angle that the enemy or thing one is facing. From that angle, it will create a vector that represents where that angle is headed in the map. It will then create another vector based on the positions of both of these things, and then it'll do a dot product. And if that projection result, that scalar, if it is greater than or equal to 0, that means that that thing 1 can see thing 2. And these enemies, they basically have a field of vision of about 180 degrees, which isn't entirely accurate, but it works for a video game, I suppose. So this is the next check that I can run. That's not very expensive. But now let's say sector has line of sight. You're within the field of view. So now things get interesting, and we then need to do a final check, which is the most expensive one, but it's still not too bad. I haven't noticed any issues with it yet. But this check will do sort of a direct line of sight, taking into consideration the walls that are between the player and the enemy. Now, when I first wrote this, I had cast a ray out into the world that would collect all the line segments from the block map as it traversed. But I realized that was a bit more expensive to do, and I found another way to cheat a little bit. So what I decided to do instead is not be too concerned with what's in between an enemy and a player. What's immediately around the enemy, what's immediately around the player. So if we want to map this out as an example, we can take this here, where this is where the player starts in the demo I just gave, and this is where one of the enemies are. By the way, if you haven't seen any of the other videos, the reason why you see, if you can notice that, but the reason why you see Doom characters here like imps and Doom guy is because I'm building this level data using a WAD editor, and then I wrote my own WAD converter, and then my engine takes that data and then rebuilds all the 3D from it. But so you have this enemy here. If I were to draw a vector between the enemy and the player, this is how I determine direct line of sight. I take the the walls, I should say. It's easier to talk about. I take the walls that are in the sector that the enemy is in. So that would be like here, right? These guys down here, just the walls. And then I take the walls that are covering the player. You can see the break in the sector here. So it would just be these two. And I check if there is an intersection between this vector and any of those walls. Now, a lot of these tests, they get discarded very early because I check the lines x and y extents. So for example, if this vector is completely above another line segment, like this one down here, that test just instantly gets discarded. There's no real math that has to run for that. Or like for this line here. But when it gets a little tricky, like you see, this wall here is intersecting. I mean, it's easy for your eye to see it, but this is a maybe for the program, right? These are maybes for the program. Then it runs through a more complicated math operation. But really what it's doing is there an intersection? So in this case, down here, when it's checking the first sector, if it finds that there's an intersection here, then it's just going to stop. It's not going to continue. If this wall was not here, then it would be able to see you. So there is a slight issue with this, though. It means that if there's something in the middle between this ray being cast, between the two sectors, then the enemy is going to see you no matter what. But that limitation is being done for performance. So in the case of the enemy up here, if we were to draw another ray, okay, like this, the only reason why he can't see you is because of this wall here. And, because there are no walls immediately around him. If the player moved to this sector here, then again, this wall would be blocking you. But let's say the player moved out into this area here. And let's just say that I had a wall. These colors are getting confusing, but I had a wall here. Well, unfortunately, he will see you because the sector that this enemy is in, which is this grid, has no walls, so it won't detect anything. And then there are no walls blocking you in this sector, so he will see you. So it's almost like when a level's being designed, as long as the level designer understands that, they would be able to build the levels and place the objects where that should not matter. But it runs a lot quicker this way. And so it was just a decision to gain more performance and not have perfectly accurate sight for enemies. So if we look at that line of sight code, so this is sector 1. By the way, I have some refactoring to do. Some of this code's a little sloppy, but you throw in thing 1 and thing 2. So here's enemy and here's player. This line segment, line A, is that vector between the two things. So that's say this vector or this vector. I grab the sector that thing 1 is in, and I loop through all the line definitions, and I only consider walls. So those would be lines that are not two-sided. And then line B is that wall. So it loops through, for example, all these walls. These walls individually become line B. And then I call this my function line intersect. And I do this for the sector that the enemy is in, and I do it for the sector that the player is in. If we look at line intersect, I try to first end this check as quickly as possible by just checking the extents. So I talked about that a second ago, but just to visualize it, you can see if you're comparing this vector here, this green vector, with this vector right here, this part of a wall here, well, the y positions and the y position of this vector, which let's just say y1 and y2, they are completely above the y components of this vector. So there's no need to ever check for a collision. It's never going to intersect. And so I do these early checks to filter out the noise. And then down here, this looks very cryptic, and it is, because it's trying to it's using algebra to determine if there is an intersection, where would that intersection be, and it's able to figure out if there is an intersection at all. And the reason why this is especially confusing is because I have a commented out version that was using the 64-bit math from the 3DO library, and I ended up commenting that out and just using straight multiplication and shifting to save more processing time. But you can think of this as just two expanded equations. And I'm doing the same thing down here where I filter out 64-bit math. I'm not using like the 3DO libraries divide. I'm just doing a straight division just for speed. And if I wanted to, I could return back the point at which those lines intersected. And I may use this later, but for now, if this does not need to be calculated, I don't bother calculating it. But later this can be helpful. So what I might do later is maybe you can set a flag when you call this to return the intersection point or not. So if we tie this into the state callback logic, so you see here when it's in search mode, which is defined here when they're idling, it's going to check for that sector line of sight, then the field of view check, and then finally that final line of sight check. And if all that passes, it switches into the C state, which is going to go into the chase group of states here. And if you look at chase, this is pretty cool. So what I did for now is I give the enemies a 1 in 3 chance at a certain point in their animation of whether or not to attack you. And so that just happens to be, I made it frame 5 for this test. But when it's in frame 5 of the animation, and only until then, and only once in that sequence, it's going to get that 1 in 3 chance. And if it hits, it's going to do a quick check first to make sure that you're still within the line of sight. So it won't take a shot if all of a sudden you run behind a wall. So it makes them appear a little bit smarter. And if you look at the attack, then it waits until frame 8 and only on frame 8. And the reason for that is because frame 8 of this particular enemy is when you see the muzzle flash from the rifle. So I'm able to pinpoint the exact moment to play the gunshot sound and to cause the muzzle flash effect. So yeah, this is it's shaping up. What I need to do now is implement being able to see a enemy from all sides. So I need 8 angles to present the enemy at, depending on your angle to it. And then from there, I need to implement the ability for them to move around, and they're going to be referencing the block map to determine, is there a wall that I'm colliding with or not? And let's see, one last thing to mention is this noise level. So the weapons, I believe what I did for the weapons is they have a noise level. And right now it's just any noise is enough noise. But as these sectors are being batched up for processing, the engine knows if there are any enemies to also process. And if there's an enemy that is idle, it checks to see if it heard any noise. If it did, it immediately goes into its chase state from there. And when you fire the gun, I grab the noise level from that gun, and then that's what gets determined. Now later, it could be more complex where there could be like a formula that determines, maybe based with distance, and what the noise level of the weapon is. Did the enemy hear it or not? So this can get pretty interesting later. Or maybe you have a silence weapon and that noise value is 0. But if you look back at the states, it checks the noise level, and for now, if there's just any noise, it immediately bypasses all this line of sight code and just goes straight to chase. And this is a bit of a blessing, because if you make a lot of noise, if you're running around making a lot of noise in the game, the performance should be even better, because it won't have to process as much to figure out if you're around an enemy. But let me demonstrate the noise, because I'm not sure if I showed that. All right, so I'll stay in this hallway where they can't see me, and I'll just fire the weapon. And now you'll notice he's already animating because he's active. This dude's active, and this guy most likely heard me too. He's already active. But these guys were too far away, so they are not alerted yet. There it is. This guy over here, he doesn't know I'm here yet, but now he will if I fire. There you go. And I might actually do like a chain reaction, like, well, if an enemy fires, well, that makes noise too, right? So maybe if this guy fires his weapon, it wakes up the guy over down the hall. So I'll play around with that. This is something that I don't believe Killing Time had, along with, at least for this enemy type, along with only taking a shot when you're within their line of sight. So I think that's a couple of improvements already between the engines. But I hope you enjoyed the video. I'll be working on this some more and keeping everyone updated on the progress. It's starting to shape up and get a bit exciting. So I hope you enjoyed, and Happy New Year.